So, welcome again to the talk. What I'm going to talk about today is how to scale up blockchain performance, or how to scale up blockchains and improve the performance of the blockchains. And there are various ways of doing it, and I have picked up just one way and I'll discuss about it. So currently, we have a very poor scalability as long as blockchains are concerned. So Bitcoin is about 7 transactions per second, whereas if you look into the existing financial payment service providers, for example, Visa has this big number. Transactions per second, I'm not very sure of the numbers, but this is what is reported on the web. So why is this slow? Why are blockchains slow? And that has something to do how the blockchain system works. And if you notice that the steps that are involved to commit a transaction, then there are several steps. And the first step is that if you are making a transaction, you would want, so the simple example is that A wants to send some funds to B. And when you do this, then you have to put this transaction in a block. But in order to do that, you have to broadcast this transaction in the network. And then, that takes time. And then the nodes have to collect these transactions together, combine them, put them in a block, try to mine, which again is time-consuming process. And then it is sent to the blockchain network, and it is added to the blockchain, or sometimes this might be a bit delayed. Some blocks might be dropped, and Bitcoin essentially says that there should be 6 confirmations. That means that if you have the transaction in a block, then the transaction is confirmed only if you have enough confidence, which means that you have 6 more blocks on top of the block that contains the transaction. So all this makes the system very, very slow. The main reason is that you have to, as I mentioned last time, that you are doing consensus at scale, which is a very, 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 very time-consuming process. And this entire thing gives us very good guarantees. I will not say guarantees, but it alleviates several problems. But at the same time, this whole system is pretty slow. So there is this scaling trilemma, which says that you cannot achieve scalability, security, and decentralization at the same time. And it looks quite intuitive because if you would like to have some security on top of things, then it is essentially a bit slow, because you have to do certain computation, and there would be some communication overhead which has to be taken into account. And also, when it comes to decentralization, there is a need for coordination between the various parties, and that is also time-consuming. And as the number of parties increase, this becomes more and more difficult to do. So this is actually the kind of layers that you can think of in a typical blockchain network. So at the base, you have some hardware. So this would essentially mean that whatever the communication channels, actually the physical communication channels, then the computation resources that are there with the various entities. Then you have the network. So the hardware would be the computing resources and so on. The network would be the physical communication channels between the nodes. And then you have this entire layer, which actually takes care of the consensus algorithms, the transactions, and so on. So this is all the algorithmic layer where you have various transactions, where you verify the transactions, where you create blocks, where you run your consensus algorithms. And at the top, you have the applications. It could be some payment application, or it could be, transacting on electronic, transacting or sending a file across the network. It could be, having medical records being verified and so on. You can think of hundreds and thousands of applications. The important thing that we need to do about the scaling is that how can we have faster consensus algorithms in this layer, and how can we have some kind of applications specific methods of scaling. And the most prevalent ones nowadays is to have transactions off the chain, because as we saw in the previous slide, the most time-taking part of the entire blockchain system is that you are interacting with the blockchain. You are not just interacting with the nodes themselves, but you are interacting in the blockchain. You are writing to the blockchain. Whatever information you are writing on the blockchain, that is the communication overhead. As much information you are writing, you are actually sending out information, and that is actually increasing the communication overhead of the system. But that is required, because you have to for every transaction, for everything you are doing, you are actually touching or hitting the blockchain. So what the general way of dealing with it is that, can we do something off the chain so that I do not hit the blockchain for every transaction, but I do it offline, off the chain, and then there should be some guarantee which says that whatever off-chain transactions you have done, it is actually correct. It's even without the help of the blockchain, you can verify that the sequence of transactions that you have done is perfectly fine, or this works and this is a correct sequence. And these are the correct transactions. So during this part of the talk, I will be talking about, firstly, the payment channels, which are an off-chain mechanism of scaling networks or scaling blockchains. And then I will talk about just one application that actually uses this payment channels to make things faster. Just as a note, I would like to mention that there are various off-chain type of transactions are taking place, and these have been deployed in practice, and there has been a lot of speed up that has been obtained by deploying these type of scaling techniques into blockchains. What I will not be talking about is the other whole class of strategies which I mentioned about consensus, that requires a different, that requires actually different sort of techniques. Not only that, it requires various ways of achieving consensus. And one of the things that people are talking about is a sharding, which actually is not covered during this talk. Just as a note, there is a very nice survey of chain transactions that you can find on ePrint. So this actually tells us that people are essentially trying to do this and build up various types of systems that would actually work in practice. And if you see that there is something that I'm calling payment channels, and there is something called state channel. So blockchain, when it started with this whole phenomena, there were only cryptocurrencies being transacted, but it is much more than that. You need to transfer any kind of digital asset that is what you require, or that is what you would love to have, and that is not simple transaction of cryptocurrencies or payment. So you need different types of, so if you think of a simple, very, very simple example, that you are sending a file from the sender is sending a file and you are getting payment. This itself is a very, very complicated phenomena. And why is it so? Because if A sends some, A expects a file and B expects some money in return, it can so happen that A sends the file but B does not pay. Oh, sorry, if A is the one who is sending the file, it would want something, the money in return. So B is sending the file and A is sending the file and B is not giving the money. And this problem is a very, very, even a very simple problem. It's a very, very simple problem, but there are no perfect, I would say, no perfect solution. If you think that I am sending the file to you and no one else should get any information of the file and I should get the money that I deserve for the file. And this is something, it's actually a problem much more complicated, and it's about a fair exchange. Fair exchange. So I get money and you get the file. And no one else, apart from both of us, should get any information of the file. If we add this criteria, then it becomes very, very complicated because, as I mentioned, that you can get the file but not pay the money, and there is no way of preventing it. Or if there are ways and means of dealing with this problem, but then you have to leak some information about the file in order to validate that who is correct and who is wrong. Because you cannot claim to receive the file and say that, no, I have made the payment, but it did not reach you. No. That's not quite acceptable. So, I mean, with that background, it is very, very important that we not only have make payments faster, but any kind of digital asset exchange or transfer should be made as fast as well. And that is why the traditional way of sending off-chain payments has now been extended for general types of transactions. And that is where there is a new class of system that has come up, which are called state channels, and the generalization of it is the generalized state channel, where you do not have to design these protocols for every different application, but you will have a generic framework for doing that. And you can see one thing over here which says networks, and I'm going to explain why this network is coming into place. But first more about what is a channel, because I have been saying this word very frequently now. So the main purpose is that you have Alice and you have Bob, and Alice wants to send some money to Bob. Okay, this is a very simple transaction. But it's something that, Alice does not want to send it at once, but she wants to send it, say every month. I'm actually paying my tuition fees in my school every month. So it's that it's a recurrent process. So if that is the case, then instead of writing to the blockchain for every transactions I make, is there a way to make the transaction in some way so that all this information is written at the end of the year for the 12 transactions that I have paid every month? But in doing that, it's that, why are we doing it on the blockchain? So that it is verifiable, right? There is a record of what has happened, and everyone can verify it. So that is the main purpose. So if we have to do that using this every single transactions, we need a mechanism that will essentially verify that all these sequence of transactions have taken place and that no one has cheated in this process. So Alice cannot claim that, yes, I have sent you the money, and Bob cannot claim, no, I have not received the money, or the total amount, or as much as Alice claims to pay, or as Bob claims to receive. So if you have to make n transactions like this, you have n writes to the blockchain, and then it's a pretty slow process. So can I do better than this? Can I do better? So that is the main question to ask. And I am doing this off-chain, and I will make less writes to the blockchain in doing these transactions off the chain. So what will I do? I will essentially make just 2 writes, maybe at the first and the last, and that's it. None of these transactions in the middle will be written on the blockchain. So that is the purpose. That is what I would like to do. I will say that yes, I'm starting a transaction, I'm starting a sequence of transactions. Okay, at the end of the transaction, I'm over with the transactions, and then everything should be balanced. Okay. Now, if that is a requirement that I have, then I need some mechanism to do that. And that is where the payment channels come in. So I will start with a very simple construction of a payment channel, and I will keep it very simple. I mean, there are various notions, but I will start with the simplest one. So this is a unidirectional channel, and what it means that only Alice is sending money to Bob. So what happens is that Alice and Bob, they actually open a channel. What is opening a channel? So Alice sends some money to an account which is a joint account, you can say, in a very simple terms. And you say that yes, I have opened, say, a channel of 1 BTC with 1 BTC. So Alice actually commits 1 BTC and says that yes, look, blockchain, it writes this in the blockchain saying that I am opening a channel with Bob and I'm depositing 1 BTC on this channel for the moment. So what does this mean is that in order to spend this 1 BTC, both Alice and Bob should come together and have their consent. Okay? So typically, this is what it actually, okay, so this means that so this means in order to spend this 1 BTC, both Alice and Bob should have to sign. Okay? And if in order to do this, you could actually say that, you know, I'm making various transactions. What is this? What does this essentially mean? And how does it really work? So it says that in order to spend this 1 BTC, Alice and both must all sign. But if, you know, no one is claiming or nothing is happening, then after a certain period of time, this money actually comes back to Bob. Okay? And Bitcoin and the various other cryptocurrencies have this amount which says this is a lock time, and it says that after this amount of time, you can get back your money if it is not spent. Or you can actually say more than that, which I will say in the next few seconds. Now, this is actually what is happening. So if Alice wants to send just say 0.1 BTC to Bob, so 0.1 BTC to Bob, then it carries out this transaction. So this is the transaction that is to be made. So this means that this amount is spendable. So this will be sent to Bob, and this will be sent to Alice, meaning that Alice can spend this transaction, spend this amount now, and Bob can spend this amount now. So these are the spendable amounts that actually Alice and Bob will have. Now what happens? In the next part, again, Alice wants to send, you know, some amount. So what happens is that it creates another transaction with this amount. So essentially, Alice wants to make 2 transactions of 0.01 BTC to Bob. So what it will send is that it will send 0.2 BTC to Bob and this 0.98 BTC to Alice. Why does it do that? It does that because if this is all that Bob wanted, just 0.02 BTC, then what it is going to do is that you could not have two transactions at the same time because that is double spending. So only one of these transactions can be committed. And now what you can possibly do, if Bob wanted 0.02 BTC, it can simply stop this over here and commit to the blockchain. Or what it can do, if it wanted one more transaction, then this transaction would look like this, because I don't want to do any kind of double spending, so only one amongst this transaction will be actually committed to the blockchain. So I can choose to do this, in which case Bob gets 2 BTC and Alice gets 0.98 BTC, which is actually proper. Or if Bob wants 0.03 BTC, it is in its interest to actually commit over here. So all these transactions are made in such a way that you cannot commit all of them together, but you have to commit one, and it is in the proper interest of Bob to receive the entire amount that it wants, which is actually 3.3 BTC, and that is where you can commit this on the blockchain, and now everyone is happy because that is what Bob wanted and Alice had to pay. Now, simply stated in this way, there are various things to be taken into consideration when you really have to even achieve this. And I'm only talking about the unidirectional channel case where Alice sends money to Bob. But it is not as simple as it is, because it is not mimicking the real life scenario where any party can send payments to any other party. But note one thing over here, that instead of the n transactions that I was essentially talking about, so instead of 3 transactions, I would just have 1 and 2 transactions, which are the open and the close channel information or the transaction, and that is all. So the rest of the transactions are happening off the chain. In real life, there are various other types of channels that I will not be talking about, that is bidirectional channel and the reversible channel. But for all generic purpose, for the rest of the talk, I will assume that for bidirectional channel are mimicked using 2 unidirectional channel between Alice and Bob and between Bob and Alice. Now, it is all fair, fine, if there are two parties only talking to one another, but if there are more than 2 parties, and possibly it might be the case that Alice and Bob, they do not have a channel shared between them, or it is for some reason they're unable to share, unable to create a channel between themselves. In such a case, you have to rely on intermediaries or intermediate nodes in order to establish a path from Alice to Bob. So if Alice has a channel with Carol, and Carol has a channel with Dave, and then Dave has a channel with Bob, then you are all set. You can use this path to make a transaction from Alice to Bob. Okay, so the problem is solved. This is actually a very, this problem recurs throughout the communication where there is no direct communication between 2 parties, and you take a roundabout way by finding a path between the 2 parties. It is a well-known problem of, lot of things are involved, as I will talk about this problem in a while. Now, what happens is that, it all seems fine that Alice sends 0.1 BTC, and if you have an intermediate node Carol forwards this 1 BTC to Bob, and Bob does this to Dave does this to Bob, and it looks all fine, but in reality, anyone can deviate from the protocol and refuse to forward the payment. Okay, and for various reasons. Why will I make a payment in the first place? So Carol might deny to forward this payment, and then Bob might claim that, I haven't received this 1 BTC that Alice has sent. So there must be something happening in the middle. And how do I figure that out? So that is a question we ask. So note that the transactions are not written on the blockchain, so there is no way to prove that this is happening actually happening, or we don't know who is telling the truth and who is actually lying about the thing. So how do we guarantee that everyone cooperates in this network? So this is a question. And if you look back, this is not a question of payment channel. This is a question for all networks. If you think of communication networks as in general, there is the same problem. I have to send a message from the source A to the destination, from the source S to the receiver R, and then there are intermediate nodes. I mean, why will intermediate nodes forward? It is actually wasting their energy to actually forward. So typically, nodes might not cooperate. It's not just a problem of a payment channel. Just to make the point. I'm making this point because I have something more interesting to say. So this guarantee that we need comes from a couple of things. Firstly, we need some kind of one of the things we need to do is that give some incentives to nodes, incentive to nodes to do this task. Okay, so this is one of the things that is really important, not only for the payment channel, but any communication channel you can think of. But even without the incentive, I mean, what is the scenario? Let's try to figure that out. How can we do this? So suppose suppose Alice wants to send a payment of 0.1 BTC to Bob, as before, as we talked about. So what Bob does is that he chooses some random R, and then it sends this information to Alice. So I will actually say, I mean, why I'm doing all this. So essentially, the main idea is that I will be forced to send the money. So that is the whole thing that I have to do at every node, that I will be forced to send the money, else I will lose. So in order to do that, this is what we do. Alice chooses R and sends this information to, Bob chooses R and sends this information to Alice. And what Alice says is that it actually enters into a contract with Carol, saying that, look, Carol, I will give you 0.01 BTC if you know this R such that HR is equal to Y. So over here, Alice gives to Carol, signs a contract with Carol saying that I will give you 0.01 BTC that you can spend only if you give me some R such that the hash of R is some value Y. So I will give you Y. So you have to give me R, which actually hashes to this value. So essentially what we are trying to enforce over here is that Carol should have some information with her in order to claim that money. Okay, so this is something that we want. And similarly, Carol enters into an agreement or a contract, or does a contract with Bob, saying that, Dave saying that, Dave can spend it only if it knows R. So unless and until Dave gives this information about R, Carol will not release the money or release this 0.01 BTC to Bob so that Bob can spend it. And this is the same thing that Dave does with Bob, saying that this is the contract and you give me R and I will give you 0.01 BTC. So that is the way, that is the type of contract they enter into. When I say contract, yesterday I talked about smart contract, so it is actually fully automatic. I mean, it is a contract, as in just a sequence of. It's just a logical statement which says that if you give me, so there is a trigger, and this is what will happen. And later I will show how blockchain comes into this picture and why this, again, yesterday I mentioned that blockchains, I mean the contracts on blockchains is a powerful technique. So this is the contract. This is the contract between Carol and Dave. Dave can spend it if it knows R such that this Y is equal to HR. Now what Bob will do is that, so, I mean, what Alice and Carol do is that they lock this money of 1 BTC, which can be opened or spent only if it receives R. Okay, so this is actually kind of a locking phase. And then to get this 1 BTC, what Bob will do, Bob will share this information about R to Dave, with Dave, and Dave will actually release this money to Bob. And then, so it will give back 0.1 BTC to Bob. And similarly, now that Dave has this value R, it can claim this 1 BTC from Carol and so on with Alice. So ultimately what has happened is that Alice has essentially sent this money to Bob and it looks all fine. But is it really fine? Possibly no. So what happens if this, if Dave essentially does not want to disclose R? So it has received R, but it does not disclose this R. So it holds up the channel for, say, you know, very, very long time. It does not give. So there is no way to redeem this value from this Alice. And if Alice and Carol close their channel, then Bob can redeem the funds, and then this does not work. So if they close their channel, you know, nothing works over here. So in order to do this, in order to protect against this sort of misbehavior, as in holding the channel for a very long time, there has been a concept of time lock, a timeout. Or what does timeout say? That you have to give it within this prescribed amount of time, else I get back the money. So that is the whole concept. You cannot hold this this R. You have to commit R. Or not commit, you have to give this value R, and you cannot hold it for an infinitely long time. So if that is the case, then it says that, you know, Dave, you give me this R. If you do not give me, then there will be a timeout. So, you know, you will not get this 1 BTC that you, I mean, after that, I will not going to hold it anymore. So you are going to lose on the 0.1 BTC that you should have been getting, right? So this is not a very good strategy for Dave, because it knows that if it holds beyond 2 days, then it is going to lose that 0.01 BTC that it should be getting from Carol. So this is not a good strategy for Dave at all. So this amount returns to Carol, and then, you know, whatever Alice and Carol does is their problem, but by cheating or by misbehaving, Dave does not get it. Dave in fact loses on this. Yes. Oh, sorry. Yes. Question. There is one more. Yeah. Yeah, I'm coming to that. I'm coming to that. I have not yet added the incentives as of now. Okay. As of now, there is no incentive. Question. Yeah, so if anyone deviates over here, then you make a call to the blockchain. So, I mean, if you want to settle any dispute, then you go to the blockchain.
But what is written on blockchain?
No, nothing is written on the blockchain, but you are actually taking the help of the blockchain to verify. So, this is happening off the chain. Any deviation at this point is actually being settled, or any kind of dispute settlement is done using the blockchain. So, if you think of it that if there is a dispute, then you have to say what the dispute is, and that is where you are going to the blockchain and essentially you are saying that yes, this is what I paid and this is what I received. So as of now, with this protocol, you are not actually going to the blockchain. But if that has happened, if someone says someone is not happy with the decision, then you will take the intervention or take the help of the blockchain.
Is there any information about R of the blockchain right now?
Yes, I'm coming to that. At this point, there is no information of R on the blockchain.
Because transactions are written on blockchain.
Pardon?
Transactions.
No, so then the question is, what happens is that, how does Bob over here, how does Bob and Dave, they have to figure out, I mean, suppose this Bob has given R, and say, Dave says, I'm not happy. I mean, you did not give me R. So the thing is that then what happens is that you go to the blockchain, and then this protocol will be entirely aborted because someone misbehaved in the middle. Misbehaved in the middle. No. I mean, this blockchain will actually abort this entire payment.
So then now Dave's purpose is solved. I mean, Dave wanted to disrupt, he didn't want more.
Yeah, that is what. I mean, there are certain issues with this type of whole payment channel thing. I mean, I'm not saying that this is without any problems, and I'm going to talk about these in the next few slides. Okay. Okay, so yeah, I'm coming to incentives. This was the same question with Arpita. So this money gets returned to Carol. Okay, so note one thing over here is that R is known to Dave. R is known to Bob, and same R is known to Alice. So later on, I'm going to say what problem this can create by having the same information to be known to all these parties. So over here, what happens is that if Bob does not disclose R, then it cannot spend. Oh, okay, I did not go through this slide. Now, how does this entire thing work now? So there is a timeout of T between Bob and Dave, which says that if you do not give the money within T days, I'm not going to, I mean, if you do not give me R within T days, I'm not going to give the money. And then Bob says that yes, if you do not give me, I mean, between Bob and, between Dave and Carol, it says that the timeout is T plus L, meaning that if you do not give me the money within T plus L time, I'm going to, if you do not give me R within T plus L time, I'm not going to give you the money, and so on. So essentially, what we have to do is that we have to have this timeout in such a way that it is more than what the timeout is, and this is quite logical to see. At this point, suppose Bob is sending this R to, say, Dave over here, and now Dave knows this R, right? So R is known. Now what Dave does is that it closes the channel. It can do that. So what happens is that now Carol knows R, and it can still claim this one BTC, because when Dave is actually putting it out, it is actually writing this R value to this blockchain. So note that this would create a problem, because this means that if I am, problem later, but it still would work, because none of the funds is being held by anyone. So if it is just a problem of fund transfer, then this does not create a problem, but it will create problem otherwise. And that is what we are going to see. No one would like to have this process without having some incentive, and that is where you have some fee for the intermediaries as well. And this gives, so essentially what you have is that instead of sending this 0.01 BTC, you send some kind of incentive. It could be same for all parties, it could be different, but at every step you actually give, in the contract you write that, you know, I will give you 0.01 BTC, and this fee, the intermediary's fee is actually F. So if you have this, you will simply modify the contract to include the fee for the intermediary. So at this point, I will take a small detour and mention that even for any kind of small payments, I should have mentioned it in the beginning, any kind of payment that you make, you always pay some transaction fee. Yesterday I mentioned that even in Bitcoin system, for every transactions you have a transaction fee in the, you include some transaction fee in that for that transaction. Now, if you think of very, very small transactions, this is not a very good way of going about, because if you have a very small transaction and you are paying again a transaction fee, then nobody would like it. So in the payment channel, if you just look at two-party payment channel, you know, there is no such thing that you really have to do, because you do not have to incentive or give incentive to the blockchain peers for anything. So you actually save on the transaction fee as well. But however, this is a payment, you have a payment path, so you have to give some incentive so that people forward your payments or, you know, help you in the payment process. So naturally, there are various challenges when it comes to designing such a system. And there are two broad directions to it. So you have now two things to keep in mind. You need some kind of an optimal strategy. When I say optimal, forget about optimal. Even if you want a good strategy, you would need to do two things. First thing is that if you have a very large network with many, many nodes, and they have various interconnections, it is rather important that you actually send in the maximum payment that you can possibly with minimum fee for the intermediary. I mean, from the senders or the designer's perspective, you would like to have it. And also, where there are thousands of transactions taking place all at once, you need to ensure that the maximum number of transactions are successful. Okay? So it's not just one path. You will have many, many paths like this, many, many transactions. And what you would like to do is that have as many transactions to be successful as possible. So this is a problem of, you know, traditionally, if you look into the traditional literature of networks, this is actually some kind of, you need some efficient algorithms to route the, to set up the routes between the sender and the receiver so that all your transactions get fulfilled. Why? Why do we need routes over here? So it comes to this problem where you can think of the whole network as a graph, which and over here it could be a directed graph, where you have every node has some capacity. every edge has some capacity. And it is actually the payment that has been deposited, and that is the channel capacity that you would have. And now the problem essentially boils down to a graph problem where you have a graph with, with weights and possibly directed if you are considering the unidirectional case, and then you will be sending out payments. You would like to have as many payments to be successful, pay as little fees as possible. And I'll take that question. So it is essentially a problem of optimization. Question?
So is there any requirement that the transaction amount be greater than the incentive? Otherwise, the person in between will have no interest in getting the transaction price.
Yeah. I mean, of course, I mean, this is a very logical thing to have. Right point. So this is actually an optimization problem of which route to select if you are routing one transaction, if you have multiple sets of, if you are a set of transactions, how many, I mean, which transactions would you like to be successful, and what would be your priority, so on and so forth. So ultimately, you are solving a graph problem. There are a couple of other problems that are there. One of it is the privacy problem that I did not mention about. And what it means to have privacy is that I would want privacy at different levels. I would want no one to know that, this is the amount that I'm transacting. I am actually transacting, or I am sending this much amount between two different nodes. I'm being a part of a route, because why are these important? Because an adversary can launch various types of attacks and on this network if they know how much money is actually passing through the nodes. So this requirement privacy, which I will break down a little bit and discuss in details, is a big concern for this type of payment channels as well, because no one wants payments to be known to everyone. So I mean that is something, and I will show that the previous scheme did not have privacy. So the literature as it stands now has different classes of problems. And there are people who are looking into the routing algorithms for these type of networks, and there is a class of, there is a group of researchers who are looking into the payment algorithms, which actually guarantee that the payment will be successful and then the privacy is preserved. So when it comes to optimization, it says, given a payment channel network, now you have a network, which is a graph, and how to route a payment through the shortest path, because if you have the shortest path, you would possibly pay less transaction fee, assuming that all nodes are charging equal amount of fee. Given the payment and the set of, given the PCN and the set of payments, how will you find the route such that the maximum number of payments are successful? You could have another version of it which says the maximum value of payment will be successful. So these are all, various problems that can be derived from classical, network or network optimization problem. So if you have a payment, how to minimize the total fees, so on. I mean, if you have different nodes charging different fee, how do we minimize the fees and so on? And if you look into this work, algorithmic blockchain channel design, it says that what would be a good strategy from the designer's perspective to design such networks for optimizing various matrices. This is one direction, okay? Why I'm saying this is one direction, because there are two things I would like to talk later. The other direction is that of privacy, and if now I'm going to define what I would just try to say the requirements of privacy. One of this is the link privacy. So it is difficult, or it should be difficult for an adversary to determine the credit available between the links. Sender privacy, you should not know who the sender is, who the receiver is, and what is the value you're actually sending across a channel. I mean, no adversary who is actually looking into the network from outside can know, or I will not know what value is passing through another channel that exists in the network. So these are things that I don't need to figure out how to achieve these requirements. So the construction that we had earlier, it does not actually guarantee this, because if you take two nodes, they can actually communicate and know that they are part of the same network because they share the same value of R. So R is common, so the payment paths are revealed. Now, if you look into this network, there is another type of attack which is called the griefing attack. And this says that if you have this kind of the HTLC that I talked about, the hash time locked contract that I talked about, you would have the timeout periods, but if Bob does not receive within this 1 day, what will happen? What will happen? It will just be stuck over there. So everyone's money is locked at that point. So there is another type of attack that is present, which is called a wormhole attack. And this is the scenario that we have. We have Alice, we have Bob, and now we have fees in the, you are giving fees for the intermediaries. So Alice gives, say, ultimately Alice and Bob wants only 7 BTC or whatever, 7 rupees, $7, whatever you say. And what it does, it says that Alice sends this money to Carol, and okay. Alice sends this money to Carol, and you have, she sends 10 BTC because she knows that there are intermediaries in the middle. How will it know? There is already an existing payment path that has been discovered by a routing algorithm. Okay, so this is an assumption I'm making here. I have run a payment algorithm, routing algorithm. I have found out that this is the path from Alice to Bob. So this is with this information, I'm starting the second part, which is the payment. So routing, so the payment follows routing, and you already know the path when you start with this problem of setting up the HTLCs. So you have 10, and you have 4 nodes in middle. You will have some incentives to give, and yeah. Maybe could have done with 3. Okay, so hold on. Oh, sorry. So now this is for this 4 is for the time lock. So this is t minutes or t hours or t days. It has to wait. 4 days it has to wait. Now it sends this money to Carol, and Carol sends it to someone called, say, Fanny or something. I don't know. I cannot think of a name. And she should get 1 BTC as a transaction fee, and this is the timestamp that I said that you have to decrease the timestamp at every step. So this is the way the whole transaction, or the whole, not the transaction, but the whole contract is set up. The simple way is that this Bob chooses R and sends it over here, saying that, you give me, everyone says that you give me R and I will give you the money. Now, what happens is that if you have Carol and Dave being malicious, they can actually do some, I mean, what can they do? They can get this value from R, from Bob, this R from Bob, and then Bob simply gives the 7 to Bob. Bob can give 7 BTC to, so Dave can give 7 BTC to Bob. Okay, that's fine. Now, Dave is in the possession of R. What can it do? It simply gives this R directly to Carol because it's an adversary. It's controlling both the nodes. And I mean, you simply do not actually involve in this at all. And this is given to R. Okay? This whole money is given, I mean, this value is given to R and it gets 10 BTC. Look now, what happens is that the adversary gives 7 BTC, receives 10 BTC, so it actually gains 3 BTC. But in reality, Carol should have gone 1 BTC and Dave should have got 1 BTC. So together they would have got 2 BTC, instead they are getting 3 BTC. So they are actually gaining by launching this attack, which is called a wormhole attack. So if you have L intermediaries, then you get, in this part, if you can skip the L intermediaries in between these two nodes, I mean, then between the adversarial nodes, then you get L minus 1 extra, which is actually, the bigger problem is that everyone thinks I'm fine. No one essentially gets to know that, you know, they have cheated. So this attack is more difficult to find out or difficult to detect in the network. And now I'm coming to one of the countermeasures to this sort of an attack on Wormhole. So, and this is where you have not just time locks, you have what are called multi-hop locks. So what we want out of this multi-hop locks is the same as before. We want atomicity, meaning that every user is able to release its left lock in case that its right lock works fine. So in the previous case, left means this side and right means this side. So the simple thing is that I get something and I give something. Okay, so that should work in practice. So how would I create such locks? So such that this is possible. So you want the transaction to be successful, you need consistency, and it means that no attacker should release its left lock without getting the right lock. So what was happening previously was that you have an attacker who was releasing its left lock, but its right lock was not being released. So you would like to have these two things in order to have the payment to be successful and no cheaters. Not just the payment to be successful, but also you have to keep in mind that we need one more consideration, is that no one is getting anything that they should not get. So that is something that we want. And we need some kind of a privacy from this type of protocols, as we have already discussed. So this is a paper that discusses this type of protocols. And I'm going to give you a very high-level idea of how this works. So the main idea is that every node has certain states, and it is such that you have to, in order to open the left side of the lock, you have to get something from the right side. And so if this does not make sense at this point, don't worry, I'm going to show you what it means. So this is how the whole protocol works. So I will give you the generic description of this protocol, and then I will show you some of the more nitty-gritties of this whole idea. And there are some of the techniques that I will again leave in a very high level, giving a very high level idea. So if this is the requirement that I should get I should release my left. In order to release my left lock, I should have the right lock also released. Then this is what I can possibly do. So the sender sender would actually have some, so we, in the beginning, there are certain things that we would want. We would like to have a function g, which is a homomorphic one-way function. Why we need homomorphic, I'll come to it in a while. So this will be not only one way, but have the homomorphic property, which I'm going to say in a while. So this Alice, what she does, who is a sender, she actually selects some y0, some y0, and then it computes this value using this homomorphic one-way function g. And similarly, for every node in the network, it will choose such a value yi, which is somewhat secret, and then it will compute this information. And the homomorphic property comes because at one point of time, we have to prove that gyi plus gyi plus 1 is equal to g of yi plus yi plus 1. So that is the homomorphic thing that I would require at this in this whole thing. So what I do, what Alice does is that it sends this information y0, y1 and small y1 to Carol. It sends y1, y2 and small y2 to Bob. So this is Dave, and then it sends this information. I'm going to talk about this in a while. I send simply y2 to Bob. And this is the key that will help me to open the locks. I've not talked about lock yet, but this is somewhat some secret information that I would require, just like I had some secret information R that I had required earlier. So one of the things to keep in mind and trying to bring in the differences from the previous scheme is that in the earlier scheme, all the nodes actually shared the same R value. Now you would have different values, different secrets between the individual edges of the, between the every pair of nodes. And in order to do that, these are the secrets that are very specific to each of these nodes. And what happens is that, this does not look like a secret, right? Because this is the source, the source is actually generating it, but we will see how it is used. So Alice takes this information and sends it, constructs this information and sends to all nodes. And these nodes should verify that this is a correctly formed tuple, this tuple. So what it does is that it also sends some kind of a zero knowledge proof. I'll come to it in the next part. So at this point, I will simply say that it simply checks. How it checks, I will come to the later part, come to the next iteration of the protocol. So suppose all these are well-formed tuples, everything is fine. Each of these pairs of nodes will check whether their left information and the right information of the previous node or the left node are the same. Okay? And why I'm doing this will become clear when I go later in the protocol. So with this information in mind, I'm going to make these checks at each point of time. If something, if this is incorrect, then there will be an abort question. Okay. So there are two types of channels, okay? One is for payment and other is a communication channel. So Alice has a communication channel with Bob, okay?
What are the assumptions
Yeah, I'm coming. I'll actually talk about examples that you would be possible candidates for such things.
There is already communication challenge, communication challenge between Alice and Bob. And why Alice cannot use that as a payment channel?
The communication channel and payment channels are not the same. Communication channel means, what would I say? I can talk to you, right? If I do not have your bank account, I will not be able to transfer money to you. So it's not, you can ask exactly, but that's not how actually things work, because you are not. So the channel is set up not just by knowing the address of another node, but possibly they do not want to create something, because ultimately they have to unanimously come to the conclusion they actually want a communication channel. Sometimes it might not be possible at all because they do not have enough resources to sustain a communication channel. Payment channel. Right. Okay. Fine. Okay. So then you have this this part where you need something. So this locks are created if you simply have this to equal. That's not actually how locks are created. I'm just saying that this is an overall view. I have not yet created a lock. I've set a condition where I would create a lock I would create a lock only if this test satisfies. I've not yet said that how to create a lock. But during the release phase, what happens is that this Bob essentially checks whether this Y2 that Alice sends is actually whether this relation holds. And if this relation holds, then what it will do, it will send this K3 information, this information about K3 to K3, which will actually open the lock between these two parties, and it will again make a check with this information Y1, and this whole thing that we actually talked about, because G of K3 minus Y2 is nothing but Y0 plus Y1, and so you would get this done only if you know, this would actually match only if you know this K3 is available to you, and similarly in this part and this part. So at this point, these are only checks I am making. I'm not actually opening or closing a lock. But why do you need K3 is because you would like to open or close the lock. So I have not constructed the lock as of yet. So this is the generic idea where you would that one would use to release the lock or make a lock. But then the question comes that how would I realize it in practice? Because I need construction of, I need proper lock construction, and I would need algorithms, I would need the release conditions as well. So I would need the homomorphic operations to be performed, and not only that, I need compatibility with existing cryptocurrencies. So yesterday, if you remember, something that I told you yesterday was that not all crypto protocols are compatible with the existing cryptocurrencies, and this is actually important because you cannot just choose any homomorphic one-way function and put it in here, because it is not compatible with the existing blockchain. So what I do, there are possibly two candidates, there could be more. One of it is a signature. Why am I talking of signature all of a sudden? Is because of this. Okay, I'll talk why I need signatures and this specific type of signatures, because they have the homomorphic property, and they also have, they are actually compatible with the Bitcoin. Okay. Now, one of the things that I mentioned previously was that you check whether this property is well formed or not. And this is one thing to note over here, is that to check this, I will not like to know, I would not want these individual nodes to know all the values of yi, because if this node wants to check this property, then it has to know not only y1, but it also has to know y2. But I only want him to know y2 and not y1. And that is where, when I send this information about this tuple, I send a zero knowledge proof saying that yi is well formed. Okay? And I'm not mentioning how this proof looks like, but this can be this can be constructed in zero knowledge. Because these are nothing but simply, finding the, proving that I know x such that hx is equal to y. So, without going into the details, I would just mention that it not only sends this tuple, but it also sends a proof that I know the secret information. Now, this is where the locking comes in, and this is a very nice little idea. It appeared in one of the I think Stack Exchange or some kind of a forum like that, and this was picked up by the authors of this paper, which was very nice. It says that you can lock. What I mean by locking is that I have a message, and if I know the public key, I will create a lock. And to open this lock, I have to create a signature on this message under the public key PK. So what I do is that I know M, I just construct some M under the public key PK, and to open this lock, someone has to create a signature on this message. So what do I mean open and create and open? It is something like this. If I have to spend this coin, I have to create a signature showing that I am the one who is allowed to spend. Okay? So this is the crux. So I can, if this is say Carol and this is Dave, it gets some information and it says that yes, I am the one who is allowed to open the lock, and I am the valid person. So you have to authenticate yourself that yes, you have the information, and you have the information, so you have to say that yes, I know the secret key that will actually open this lock. Okay, so it is the same thing that we were doing earlier. Earlier you were saying that I know x such that y is equal to hx. Now you are saying that I know some secret information so that I can open this. Why am I doing all this? Is because not only, to find a good construction, as is also a scriptless. Scriptless in the sense, it is actually also compatible with the Bitcoin. So this is the locking that has been talked about, and in this very specific case, the way it goes is that if ui plus 1 and ui plus 2, so these are 3 nodes in the network. So what you have to do is that you get some information, some secret from ui plus 2, and ui will be able to use the secret information to say yes, give that money. So if you have ui plus 1 gives some secret information to ui, and ui gives the money, right? Similarly, ui plus 2 gives some secret information to ui plus 1 and gives the money. Okay, so this is the generic idea, and now what you do is that you need to do this locking and unlocking. So you have to, in order to get the money, you need to unlock. So that is the main idea. Now, if you have ui and ui plus 1, what you do is that they will together, combined, in a combined effort, they will try to create an incomplete signature sigma dashed. And sigma prime is an incomplete signature on M. So how they do it is a different story. I'm not going to talk about that, but intuitively, it will only create an incomplete signature which can be made complete only when ui plus 1 has some information from ui plus 2. So this signature would be complete only with some inputs from ui plus 2. So in order to unlock, you need ui plus 2's help. So this is the information there would be some information that you would need from UI plus 2. So for example, if you need to open a lock on the left side with Carol, you need some secret information from Bob. Okay, so what happens is that Carol and Dave, they have a combined lock initially. They have a lock over here, which is an incomplete signature that they would like to have, and they can complete the signature when they get an input from Bob and open the lock and get the money. I mean, it's a little bit complicated. Yeah, but I'm trying to make you understand that in order to get information from Carol, Dave needs some information from Bob, ultimately. Now, this whole approach also suffers from griefing attacks. So Dave does not want to share K2. What happens? Don't know. It again gets stalled like before. And this paper claims to solve this problem. I'm not very convinced about this paper, so I'm not going to talk about it. Just a couple of notes at this point is that there is a very big disconnect between the two things at this point. So a lot of work is being done in the payment algorithm wise. A lot of things are being done in the routing. Not a lot of work. This community has not yet realized that there are a lot of problems in blockchain payments as of now, else there would be a lot of work already being done. So, I mean, the payment algorithm, there has been a whole lot of literature on this. However, this routing thing is a bit slow, I would say, and the big disconnect between the payment and routing is not a very good thing, because all the algorithms that are present in this most of the algorithms that are present in this payment domain, they will assume that there is a single path between the source and the destination, or between the sender and the receiver. That's not a very good thing, because that actually restricts the usability and the utility, or good utility, of the payment network itself. If I always restrict that there is a single path between one node to the other, I will not be able to reuse channels. I will not be able to, optimally route things, route payments. So if you have a transaction like this, then what happens if you have, say, these are the capacities, and you have a value 15 to be sent across from source to destination? Then what you do is that you send, say, 15 here, maybe 10 here, 10 here, 15 here, and then 5, and so on. So if you have such a situation, then one way of doing it is that you can create two paths. One would be from A, B, C, E, F, and the other path would be from A, B, D, E, F. So there are two paths at the moment, and then possibly you can route these two things using the payment algorithms that you have already designed earlier. Now, what happens is that I will route this using my payment algorithm that I have designed earlier, just that you saw, and it finds it goes well. I have fully been able to, send this payment. But is that all? No. It has only sent. You have only sent 10 BTC from A to F. That's not what is desirable. You have to send 15 BTC or not send at all. I mean, that's something like you have made a payment to someone, half of the payment has been made, or the party is not happy. Then you get disconnected. You get disconnected. That's not what you want. You want it to be done fully or not at all. So if you use the algorithm, the payment algorithm that I showed you in the following way, that you send one first and then the other, it can so happen that this payment passes through, but this does not because in a dynamically changing situation, it can so happen that, one of them closes the channel or something just goes wrong. So this is not a very good approach to take by just decomposing this whole thing into parts, into different parts. So what I would typically do is that if I would like to do them together, as in both should pass or both should fail. And if I use the concepts from before or the routing algorithm from before, this does not work. And why it does not work is that because the secrets that would be present would be incompatible to open the lock. And so this is an example that we have, but I'm not going into the details of it. But this will fail because you do not get the right key to open the lock from the previous node, or correct information from the previous node to open the lock. So if you want an atomic payment to happen, this is not the strategy that you would take. The point I'm trying to make over here is that by looking at payment and routing separately, you are actually losing out on the complete utilization of the network. You are losing out on that. The other thing, I'm going to take your question. The other thing is that it will not be able to, generalize, or, it will not be able to just apply the existing routing, existing payment algorithm if you have such splits and merger in the path. Okay, so because this will not work. So the question is, can we solve these two problems at tandem, and so that you have better algorithms? And some effort is being made by my student Shubhra in this direction. We have some solution for this type of results, but I'm not going to discuss it at this point. But I will just, I will break because I have a question over there. Okay, so these are not the type of payments that you are typically seeing in the simple bank transfer.
Even if we do for mobile banking or something.
No, that's fine. I mean, this is for more complicated structures where you have, you are paying in, you have a different payment structure altogether. The good thing about your statement is that you have a lot of trust in your bank. It does a lot of things. Over here, you will have many intermediaries because this is not the traditional banking thing. Questions? No, actually not. Banks do not want to be mistrusted, or they want to know everything. Banks, I mean, it's at this point, I don't know what will happen later, but no one would like to have this. So this is what I mean. I think a way forward for payment channels is to bridge the gap between both these directions, because now it is kind of divided, and that is why everything looks very rosy on this side and everything looks very rosy on this side, but unless and until we see the big picture, it might not be a nice approach to have. So I will just take 2 minutes to mention. I will just mention. I will not go through the protocols or anything, but a whole lot of work is being done, as I mentioned earlier, not just on payment, but on sending for other applications as well. One of the challenges in these directions is that for a very simple type of a payment, you can simply say that, you know, you give the payment and you give something. I mean, you give the payment channels are rather easy to handle. In the beginning of the talk, I said that, you know, when you are exchanging assets, it is a more difficult problem to solve. So one of the other directions where a lot of work is being done at this point is looking into the off-chain transactions when it comes to exchanging digital asset. And the problems, there are similar problems over there. There are problems of fairness. Everyone should get whatever they want or what is there in the contract. In those cases, it is not just the Bitcoin type of contract. You can go into complicated smart contracts. The reason why all this is important, or the way things are evolving, is that, I mean, the way why we want the blockchain over here is just that earlier also, you know, you had fair exchange possible. You would have, whenever you would like to do fair exchange, you would possibly take the help of a third party to mediate. What does it mean? If you have any dispute, you go to the court of law. You say that, you know, this is the dispute that has happened. The legal expert would want some, you know, evidence that you would actually show in order to prove whether you're guilty or not, or whether you're what you have done. How does it translate to a blockchain? The blockchain now acts as a trusted intermediary who actually resolves the disputes. The problem is that how often do I go to the blockchain or not? And the other problem is that how much do I reveal to the blockchain? Earlier what you did, whatever evidence you have, you would simply go to the court of law and reveal it, or say that, yes, this is the proof, or this is what I'm giving to you as a proof. Over here, you again need proofs to proving various statements that has been, I mean, to validate that, or that has been taken, that has been part of the transaction. But what you want to reveal to the blockchain is different, because now this blockchain is being maintained by various peers, and you wouldn't like to give all this information out to them. So there are many things that are important at this point. How do I achieve a fair exchange? How do I use blockchain concepts to achieve fairness? And when I say fairness, what is my definition of fairness? Is it something that I just give and get? Or is it that I want, I mean, between the two parties, is it all? Or do I reveal no information to, I mean, what information I'm revealing in order to get this fairness So in the end, I mean, I'm going to skip through the slides here, but just like yesterday, I will put in a few problems that are interesting to me and the community, and efficient privacy preserving payment channels in that direction, where you have by bridging both the gaps. This is the one, that the generalized state channels, which is actually being talked of a lot, and a lot of work is being done in this direction. So instead of just payment, you can arbitrarily use various other exchanges. You can exchange other assets, and typically the other scaling strategies that I did not talk about, a lot of work is being done in the consensus domain to make things very scalable. So with that, I will stop. If you have any questions, I will take it now.